To start today, I want you to try and have a go at this question here. Can you calculate x? Okay, hopefully you paused the video and thought about this for a little bit. Did you try and use the sine rule to calculate it? And if so, what did you notice? The issue when we try and use the sine rule is that we have this sort of side angle pair here, but we don't know what x is. But then we don't have another side angle pair. So if we take the formula that we've been using, a over sine A equals B over sine B, then, well, we can write down that x, if I call this one A into A, x over sine 105, which is sort of our normal way of writing it. If I then pick the 1.5, then I don't have, I don't know the angle. And if I pick the 6, I should notice they're in ones in millimeters and ones in centimeters. So let's say we work in centimeters, so it'd be 0.6. Then again, we wouldn't know the angle. And overall, we can't use a sine rule to deal with this. At the same time, it is possible to find the answer, and that's what we're going to be looking at today, a method for finding the answer when we don't have an angle side pair to deal with. And next lesson, we're going to look at a similar sort of situation, but where we know all three sides and we're trying to find the angle of one in between two of the sides. It's possible that the thing we're going to look at now will allow us to look at that as well. So you can sort of see non-right angle trigonometry is not just about the sine rule, there's more to it, there's actually something new that we're going to look at. And here it is. It's called the cosine rule, and today we're going to look at using it to calculate sides. A fair bit of this lesson is going to be deriving it. I don't just want to give you a formula that's come out of thin air. I want to try and show you where it comes from, and it's going to work in a similar, I think arguably more complicated way of how we got the sine rule. So here goes. This bit is non-examinable, but it's in my opinion the most interesting bit of maths, actually getting to the rule, and once you get that and you understand it, it's just a case of applying it. But the derivation for me is the really interesting bit. So I hope you agree. If not, we'll spend plenty of time practicing it. Okay, we've got a triangle, and I've labelled it again with sides A, B, C with the angles opposite in uppercase. I am going to again split it into two, and I'm going to split it into two vertically. I could do so along one of the other directions. It's just easier to demonstrate. So I've split it into two, and that has given me two right-angled triangles. I can always guarantee that. Okay, so right angle here and a right angle here. Now this time I want to write that. Before I used sine of, say, the angle. This time I'm going to find cos of the angle. And I can see that cos C is equal to, and I'm going to call this H and this A, but cos C is going to be the adjacent divided by the hypotenuse. The issue is I don't have an adjacent. It worked before for sine because I had the hypotenuse, but I've only got the full way across. So let me just call it something else. I'm going to call it x. And what that means is that this length here is going to be a minus x. Okay, we're just playing with some maths and we're going to see what happens. So cos C is going to equal x divided by b. And I might even at this point write down that b cos C equals x. Because the whole point, if you remember, for the sine rule, we got a formula in terms of h, and then we eliminated h. Now I've got x and h, but I want to somehow eliminate both h and x. I want to get some sort of formula in terms of cos of an angle in terms of the other side. So that's just there. We're going to come back to that. Right. Now, we could find cos of b and we get something in terms of a minus x and c. I'm actually not going to go there. We're going to just stick with cos of one angle this time. But what we're going to do this time is something really a bit different, and it's to use Pythagoras' theorem on the left-hand side. So before we used sine on two angles, this time I'm just going to use cos on one of the angles, and then I'm going to use Pythagoras on the blue triangle. So that gives me, I've got to remember, although we normally say a squared plus b squared equals c squared, in this case I've labelled the triangle slightly different. It's going to be that the hypotenuse squared, which is b squared, is equal to x squared plus h squared, because those are the dimensions, the triangle h and x are the two shorter sides. Does that help? It just doesn't seem to be helping, but let's just roll with it. I'm then going to do the same for c. C squared is going to equal a minus x all squared plus h squared. Okay, we'll see where we get with that. First things first, I'm going to expand a minus x all squared, and I've got to remember that that actually means it's a double, so a minus x all squared is actually equal to a minus x times a minus x. Already we've got double brackets coming out, so I'm going to get a squared minus ax minus xa, but that is the same as ax, so I'm going to write it the same, plus x squared. That's how we can expand our double bracket, and that's going to give me a squared plus x squared plus, minus a squared plus x squared minus 2ax. So a squared plus x squared minus 2ax plus h squared. Don't forget about that. And actually, although it just looks really algebraic so far, this is our first little useful thing we can do, because the first sort of simplification we can make, because I can write this as a squared minus 2a, actually, sorry, I'm going to write it as a squared plus x squared plus h squared. It doesn't matter what order I do it in, but then it becomes a bit more easy to see that this thing here is actually exactly the same as this thing here. So I can write down that c squared is a squared plus b squared minus 2ax. And I've managed to eliminate h from the situation. I've just got x left in there. But I don't, because I can get rid of it now, because I've written up here that x is actually b cos a. So the next line is going to be to replace this by this, but the thing on the left-hand side instead. So it's going to be that c squared equals a squared plus b squared minus 2a, and then I'll replace x by b cos c, and this is a useful formula. We can now relate three sides of a right angled triangle, three sides of any triangle, not a right, it could be a right angled triangle, but any triangle. It doesn't have to have a right angle, and it's related in this sort of normal way that we have for Pythagoras' theorem, a squared plus b squared equals c squared, but now I have to subtract this extra term, minus 2ab cos c. So I'm relating the angle that's opposite this side in there as well. And this is the cosine rule. And again, you must learn it. Now, hopefully that derivation is interesting. It shows where it comes from. It takes a non-right angled triangle, turns it into two right angled triangles, and just through clever algebraic manipulations constructs the cosine rule, which we'll talk about. I think let's get on and use it, and then I'll come back to talking a bit more about this formula. So, do you know what? I'm even going to come back to this. I just want to apply it. I think it's important. to do that and see how it actually helps. So we have this, we've got it written here, calculate x. This is the same situation we had before, but this time I'm going to label this little c and this one capital C. I'm then left with this side, which I know, and this side, which I know. Just going to change that 6 millimeters to 0.6 centimeters. You must be consistent with unit. You can sometimes get that. I'm not trying to catch you out with that. I just, it is important to be careful with these sorts of things. I can then write down that c squared, which is x squared in my case, let me just write that again, is equal to a squared, which is 0.6 squared, plus b squared, which is 1.5 squared. I mean, if it helps, I can write down that x equals c equals x rather. I defined it to be 0.6. I could have labeled the other one. It doesn't matter. Then b is 1.5. And then all I'm doing is substituting in, and capital C is 105. So x squared equals 0.6 squared plus 1.5 squared. I'm going to have to go onto another line. Minus 2 times 0.6 times 1.5 times, but I don't need to put the times in for this one, cos 105. And this might be the first time you've seen cos found of an angle above 90. That is okay. So we'll work out x squared. Just put it into the calculator exactly as I've written it here. I can put a times in if I want, so I don't need to. Okay, close bracket. And there we have it, 3.075. But that is only the value for x squared. So just like in Pythagoras' theorem, you have to take the square root. When the numbers are bigger, it's a bit more obvious it has to take the square root. It's not quite so obvious here because the number's not that big. 1.7538. Which we might round to 3 significant figures, 1.75 centimeters. So now you can see the cosine rule being used. That's definitely wrong, that one there. I think I accidentally used centimeters above, so I'm 100% sure that it is 1.75 centimeters. You can see that when we don't have an angle side pair, but we've got this sort of situation where we've got an angle with two lengths either side that we know, we can then work out this one. Just going to jump back to the top. So we use the sine rule if we've got an angle and side pair and one other angle or side. We use the cosine rule if we have two sides and, apologies, there's spelling mistakes here, two sides and an angle in between, i.e. no pair. Or if we have three sides, you can maybe see that if we have three sides, then actually the only thing we don't know is the angle, and we can work that out, but that's for another time. That's a whole other lesson because we're going to need to do some rearranging of the formula. For all triangles then, ABC, the cosine rule says this is true, but we know that for right angled triangles, Pythagoras' theorem says that a squared plus b squared equals c squared. How can these two match up? Well, it matches up because for a right angled triangle, this would be capital C. And if we work out what, you might already know what this is an expected angle that you know the cosine of. Cos 90 is actually just 0. So when you get a right angled triangle, this term disappears. When you don't have a right angled triangle, it's there. So this is a generalization of Pythagoras' theorem, one of the most famous theorems, mathematical theorems, ever known. Known for thousands of years. Not many theorems that that most school people will know the name of, but this is that, and this is an extension of it, the cosine rule, which generalizes and it applies for any triangle. Amazing stuff. We're gonna do a little bit more practice to consolidate this now. Before I do these examples, I've just remembered one thing. There was, just like with the sine rule, there was nothing special about me splitting the triangle down the center. Okay, the way I then did it managed to get a formula in terms of cos C. If I split it about a different line to make right angle triangles, I could create a formula in terms of cos A or cos B. And I want to show you what they look like. So for basically, you can sort of see some symmetry going on. The fact that you got A and B here, and then A and B here. If you had cos A on the right hand side after you've done your derivation, this would be what it would look like. A squared equals B squared plus C squared minus 2BC cos A. You just swap the letters around. This is also a version of the cosine rule that you could use. It's actually the one that I've taught using this many times. I've just kind of recently changed to this one. I prefer this one now because it more directly links with Pythagoras' theorem. C squared equals A squared plus B squared. And then so that is Pythagoras' theorem, and you just have to remember this extra little bit on the end. Rather than suddenly, learning A squared equals B squared plus C squared, which is not how you normally learn Pythagoras' theorem. So you might find videos of mine where I do use this. I'm trying to replace them by this one instead. If you wanted to have cos B in there, it would be almost, you just switch the letters around again. You'd get B squared, and then it would be A squared plus C squared minus. So actually, I think this does help because it helps you remember that, it doesn't really matter how you label it, in fact. You just got to remember that whatever side squared you want, it's the other two side squares added together, then you're minusing twice what they are, and then it's cos of the angle that's opposite the side you're interested in. So 3 versions of the cosine rule. My recommendation is just learn this one, unless you, because I got to admit, sometimes I get it mixed up and I make a mistake. So up to you really, but make sure you can get there. I'm going to be using this one from now on. So I want you to have a go at practicing using the formula. C squared equals A squared plus B squared minus 2AB cos C. Can you calculate the value of C given the following information? A, B, and C in each of these cases. Pause the video and give this a go. Okay, I'm going to quickly show the answers. So you should have got 7, 8.5, and 7. It just so happens that the angles I've chosen give you nice answers, final answers. You won't normally get that, but I wanted to just make some aspects simple, to be honest. So what we would do is we'd just be doing 8 squared. I'm just going to go through it. So if you got them correct, you can fast forward through this. But it's 8 squared plus 5 squared minus 2 times 8 times 5 times cos 60. And that gives me 49, which I then square root to give 7. Second one, very similar. 12 squared plus 8 squared minus 2 times 12 times 8 times cos 45. Okay, I don't get a very nice answer here actually, so then I square root. Oh, I just realized this. Okay, this one is rounded to 8.5. I thought they all came out exact, but yeah, not that one. And the last one, similar again. 5 squared plus 3 squared minus 2 times 5 times 3 cos 120. 49, if you square root, you again get 7. Brilliant. Quick applications of the cosine rule. We're not having to, deal with triangles as such here. It's just a substitution kind of part of it, making sure we can apply the formula. But if we can label the sides correctly, then it is just a process of repeating this essentially, which we'll now look at. So there's just like a subtle thing you need to be careful of in this question. But actually, I welcome for you to pause the video and give this a go. This is, by the way, this is the main bit. This is the main part of the lesson today. We spent a lot of time deriving it and talking about it. So I just want you to be able to go away now and apply it for situations such as this. Of course, you got to, in the future, you don't know, will I use the sine rule, cosine rule? You have to recognize it, but we'll get to that. We'll have mixed questions. For now, we know we're going to use the cosine rule. Give it a go. Right, I'm going to go through this. The first thing is that we don't have an angle side pair. We're trying to find this thing, this length. I'm going to call it x for the moment. No, I'm not. I'm going to get rid of that. But I don't have an angle side pair, so it's going to be the cosine rule. Now, we've learned the cosine. So I would then recognize to write c squared equals a squared plus b squared minus 2ab cos c. The thing is, I don't. This is the angle c over here, and this is the angle a. There's two options. You could write down that other option for this top one for the cosine rule, or you can recognize that actually it doesn't matter how you label your triangle. You're allowed to change the labeling. So I'm actually going to call this capital C, and I'll just swap them around. There's no problem with that. It's just helping me use the formula essentially. So now I'm going to be finding little c. And I've got all the things I need. I've got that a is equal to 3, b is equal to 7, and capital C is equal to 35. And once I've done that, I'm doing exactly what I did up here. C squared is going to equal 3 squared plus 7 squared minus 2 times 3 times 7. I would expect, I know I didn't do it above, but I would expect this level of working. Sorry, it didn't quite come out. Just temporary issues with my pen. Yeah, it's better. 2 times 3 times 7. You could just put the square root around it straight away, I like to just find out what c squared is. Yeah, I don't know, it's just a habit I've got into. So this is what I mean by, it's quite a large number, so I'm probably not going to forget to square root that because I'm going to think, oh, is that right? 23.595. So c is the square root of that. You can write that down if you like, or you can just go straight to it. 4.857 or 4.86 centimeters. Nice. Well done if you got that. We can now apply the cosine rule to work out sides. Whew, good job. Over to you. Try this exercise. Don't be afraid to relabel the triangle to make capital C the angle that you're interested in, and then little c will be the one opposite, and relabel accordingly. Of course, you can use that other version of the cosine rule. Just be careful. My advice is to relabel it. That's what I do. I just stick with one formula and relabel it. Here are the answers. 1 to 6. They're similar sorts of questions. And then here, this is a challenge question. Again, two adjoining triangles. Can you work out DC? Okay, the temporary step is that BD is 8.92 centimeters, and you get that by applying the cosine rule to this right-hand triangle. Because, sorry, it's going to be to the left-hand triangle. Sorry, cosine rule to the left-hand triangle because you're missing this side, but you've got these two here. You can see in the mark scheme. Once you've got that one, then actually we need to use the sine rule. So I'm not going to go through the cosine rule bit, but I'm just going to remind you, so this is going to be 8.92. And then we've got an angle side pair, and we're trying to find DC. So that's another angle side pair. We're just missing this bit. And therefore we can write down the sine rule. Using it, it's going to be the 8.9165 fully. We shouldn't round it. Divide that by sine 80 equals the one we want to find, divided by sine 40, rearrange it. The final answer is going to be 5.82 rounded. And one more, how about this one? Can you work out BC? Here's the answer, 8.52 in this question. So this time we have to use, right, we're trying to find BC, that's this one here, but we can't do that at the moment because we just have, well, you can work out this angle is going to be 100, but we've only got one side, that's the issue. So we need to work out what BD is. And in that situation, we need to, this time, to use the sine rule first of all, and that will allow us to work out BD. So BD over sine 45 is 7.4 over sine 80. Rearrange it and get that BD is 5.3133. And once you got that, you're in business. You're in the same situation you were before. So expect that sort of thing. It's nice bringing this kind of question where you have to use both the sine and cosine rule, and it's starting to make you think, which do you use? Whew, well done if you got all those. Brilliant effort. Okay, we'll continue next time with using the cosine rule to find angles.